And so we've discussed page replacement algorithms and how to handle the fact that we have a full physical memory and the need to replace some of the pages to continue executing multiple processes that we have in the system. So now we're going to talk about the initial allocation of frames. How can we what are the different ways to allocate frames initially to a process? So remember we talked about pure demand paging, right? With pure demand paging, we said that we're going to allocate 0 frames initially to a process until it starts page faulting with every reference, and then start loading those pages to memory. And that's not common, so usually we start with a minimum number of frames, and then the allocation schemes can vary, and we can talk about 2 main ones, whether the first is the fixed allocation and the second is the priority allocation. And so with the fixed allocation, we can either allocate equal number of frames per process. And so if you initially have 100 frames and then you have 5 processes, then you can give each process an equal number of 20 frames, right? An alternative is to use proportional allocation. And proportional to what? It's proportional to the size of the process. And so depending on, you're going to allocate frames depending on the size of the process. So the bigger the size, the more frames you're going to allocate to that process, right? Which makes sense. So if we assume that S is the size of a process PI, and so big S, of course, will be the sum of all the sizes of all the processes in the system, and if M is the total number of frames, then the allocation for process I can be equal to the size of I over the total total size of all the processes times the total number of frames. And so if we have 2 processes, that the process number 1 has a size of 10 and the second has a size of 127, and then therefore the allocation we're going to end up allocating 4 frames to the first process and 57 frames for the second process, right? Because the size of the second process is bigger than the first process. Therefore, we're going to end up allocating more frames to the second one. And so when it comes to replacing, we have the choice between local and global replacement. And so with local replacement, a process is only allowed to replace its own set of allocated frames. It is not allowed to touch other processes' frames. So we do not include those in the choice of frames to be replaced. Versus with global replacement, the entire frames that exist in the physical memory are actually candidates to be replaced. Another way to think about it, we can make higher priority processes, nice as steal away, but take some frames from the lower priority processes in order for the higher priority process to execute faster, right? Which makes sense because it's a higher priority process. So we want to give it all the necessary resources, including, of course, frames. Therefore, with global replacement, we do have the ability to steal away frames from the lower priority process and allow the higher priority process to execute faster. So we're going to talk about a problem that's called thrashing. So when a process don't have the necessary pages that it needs already loaded in the physical memory, then it will start page faulting, right? So it will, for instance, if a process needs 10 pages, but it has only been allocated 2 frames, right? Then the process will map the first 2 pages, and then when it will need the 3rd page, it will page fault and replace one of them at the 3rd reference to the 4th page, sorry. Then it will replace the second 2, and then once it will need the original one, it will page fault to replace it and keep page faulting all throughout its execution time. So it will spend more time actually page faulting and handling the page fault than really executing or doing any useful work. Okay, why? Because we didn't allocate enough frames that process needs. And so when that process is actually in this cycle of page faulting and not really executing on the CPU, then what the operating system will detect is we have a drop in the CPU utilization. And so the operating system will think, oh well, since the CPU is idle, and so we do have room to admit more processes. And so this will increase the degree, because the operating system's goal is to increase the degree of multi-programming, right? Remember, the degree of multi-programming is the number of processes that we admit into the system at a given time. And so when the operating system will detect that the CPU is not used enough, it will try to admit more processes to increase the degree of multi-programming. And so when those processes will be added to the system, they will again start thrashing, because the original problem was not the low CPU utilization, but the original problem was that the physical memory is full and the process didn't have enough frames allocated to it to enable it from continuing execution. And so these processes will again start thrashing in turn, and again the CPU utilization will drop more, and the operating system will accept more processes. And so you can see thrashing in this graph. So in the first part, this is normal because when we have low CPU utilization, the operating system will try to admit more processes to increase the degree of multi-programming. So with more processes, the higher CPU utilization get. So at this point, we do have enough memory for those processes to run and execute. However, after this point, when the physical memory is full, then the processes will enter the stage of thrashing, where they page fault a lot more frequently, and they're not using really the CPU. And so the CPU utilization will drop, and then once the operating system detects that the utilization is dropped, it will try to admit more processes to increase the degree of multi-programming, and this will cause more thrashing and will lower the CPU utilization even further. So that's why thrashing is a bad problem, and we have to do something about it. Right, so why did thrashing happen in the first place? Because processes didn't have enough frames allocated to them, right? So one possible solution, which is logical, is to provide processes with whatever they need to prevent thrashing. But the question is, how do we know how many frames those processes need? So one way or one solution is to think about and incorporate the locality model of that process. So the locality is actually that set of pages in the reference string that are actually actively used by the process. So pages 0, 4, 5, this is the locality set that the process is actively interacting with. So at a given time, in this time window, the process is actively referencing pages 0, 4, and 5, right? And at a different time, it will reference different pages, and so the locality will change in time. However, we talk about one given window. We do have one fixed locality model for that process. And so the thrashing will automatically happen when the size of that locality gets larger than the total memory allocated to that process. So if this process has been allocated only 2 frames or just 1 frame, then thrashing will happen, because you can see that in this window, the locality of the process is actually 3 frames, not 2 or less. Okay. And so we defined the working set window as that fixed number of page references that the process is currently actively interacting with and referencing and using. Okay, and so if the size of that window is really too small, it's not going to really cover the entire locality of that model, okay, at that given time. And if it's too big, then we're going to end up covering the entire processes references, and this does include multiple localities, right? So what we want is an optimal window size that really represents the set of the pages that the process is actively using at a given time. So for instance here, if we have a window size of I think here it's 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the size of the window here is 10, then the locality set is pages 1, 2, 5, 6, and 7. That's the set of pages that the process is actively using in this window. So 1, 2, 3, 4, 5. So 5 frames is a good amount of frames to be allocated to this process in this window of time, versus in this window, again, the size is still 10. We notice that the set of pages that is actively interacting with is just pages 3 and 4. And so we can allocate 2 frames in this window of time to this process, and it's not gonna suffer from thrashing. And so one strategy to prevent thrashing is to always monitor D with respect to M. So what is D? So D is the total demand of frames that we have in the system from all the processes in the system, and M is the total available frames that we have in physical memory. So whenever we detect that D, the total demand goes beyond what we actually have, which is the total number of frames that we have, then the system has to start suspending or swapping out processes in order for us to go again below M, which is the total number of available frames. And so another way to allocate frames efficiently is to monitor the page fault frequency of the process. And so we set some sort of upper and lower bounds on the page fault rate. So if the page fault rate goes above the upper bound, then we know that that process needs more frames. And so we're going to increase the number of allocated frames to that process to prevent thrashing. And once the page fault rate goes beyond the lower bound, then we know that that process has more frames than it actually needs. Okay, then what we do is we take some frames out of that process to give it to another process in need.